Okay, good day, grade 8s. I trust that you are well. Today we will discuss quadrilaterals. Quadrilaterals. So we should first ask ourselves the question, what is a quadrilateral? You might have heard about a quad bike before. A quadrilateral is a closed two-dimensional figure with four sides and four interior angles. And you can get different types of quadrilaterals. There's special quadrilaterals, and we're going to look at each quadrilateral or special type of quadrilateral today. But the first thing we should realize is that a quadrilateral is a closed two-sided figure. So let me just take a ruler very quickly. Right, okay, so I have my ruler here, and I'm just going to draw any four-sided shape for you. Right, closed four-sided shape, and that is by definition a quadrilateral. Right, so a quadrilateral looks something like this. Okay, so if you look at a quadrilateral carefully, so let me just take another color marker. If you look at a quadrilateral carefully, what I'm going to do is I'm going to construct a diagonal. A diagonal is from one vertex. Remember, a vertex is a point where two lines or line segments intersect each other to another vertex, right? So let's create a diagonal in blue as such. So just to start from the top again, I have a quadrilateral, a closed two-sided, uh, four-sided figure rather, it's a two-dimensional shape. And I created a diagonal, and what can I see here? I can see that I have two triangles, and let's recall, what are the sum of angles of a triangle? So if I look at triangle 1, the triangle on the bottom left, I can see that this angle plus this angle plus this angle is equal to 180 degrees. And if I look at the second triangle, if I take this angle plus this angle plus this angle, it is also equal to 180 degrees. So the sum of angles of this triangle, so this angle plus 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 this angle, what will it add up to? So basically it's 180 degrees plus 180 degrees, and you guessed it, the sum of angles of a quadrilateral is 360 degrees because it's 180 degrees plus 180 degrees. So what can we conclude? We can say the sum of angles of any quadrilateral, of any quad for short, is 360 degrees. And that's actually quite important when we look at geometric figures as well. So I'm just going to use my free hand just to save some time and draw a quadrilateral, something like that. I did not give this quadrilateral a special name, but let's name it quadrilateral ABCD. ABCD, right? And let's say this angle is 100 degrees, right? Let's say this angle is 60 degrees. Let's say this angle is 110 degrees, and let's say this angle is x. And I ask you to solve for x. Solve for x in this from this geometric figure. So all I'm given is I'm given quadrilateral ABCD and I'm required to solve for x. So given our knowledge that the sum of angles of sum of angles of a quadrilateral is 360 degrees, I can use that knowledge to find the value of x, which is angle B. So I'll say x. So firstly, I know that angle A plus angle B plus angle C plus angle D is equal to 360 degrees. And remember, in geometry, you always have to give a reason for every statement that you write. And the reason is sum of angles of quad. So angle A is 100 degrees, angle B is x, angle C is 110 degrees, and angle D is 60 degrees. And that is all equal to 360 degrees. So what is this? 100 degrees plus 110 degrees is 210 degrees. 210 degrees plus 60 degrees is 270 degrees, is equal to 360 degrees. So I'm going to take x Remember, this is just a simple linear equation. I'm going to take 270 degrees to the other side. When I do so, the sign changes. So it's equal to 360 degrees minus 270 degrees. X is equal to the difference of that, which should be 90 degrees. So technically, this is a right angle triangle. So if I take 90 plus 100 plus 60 plus 110, that gives me 360 degrees. So we just proved that this is actually a 90-degree angle as such, right? So that is the first thing we know about a quadrilateral, that the sum of angles of a quadrilateral is equal to 360 degrees. Now let's look at each type of quadrilateral that we have. The first type of quadrilateral that we will be talking about is a, let me just scroll this up. The first type of quadrilateral that we have is a parallelogram. Well, it's not the first type of quadrilateral that we have, but the first type that we will be looking at today. So a parallelogram, what word do you see in the parallelogram? In this word, parallelogram. I see the word parallel, right? I see the word parallel. And another word, because parallelogram is such a huge word, it's quite a big word. Another way I can write parallelogram, I can call it a palm, or I can write the parallel sign with an M on the top, right? So a parallelogram, let's look at the properties of a parallelogram. So with a parallelogram, I can define it. Let me give a formal definition of a parallelogram. I can actually define a parallelogram. It is a quadrilateral. It is a quad with opposite sides parallel, with both pairs of opposite sides parallel. And I hope that I do not forget to tell you, right, some of the properties that we can use to prove that a quadrilateral is in fact a parallelogram. But for now, let's look at the properties of a parallelogram. So parallelogram, we said it's a quadrilateral. Let's just quickly draw a quadrilateral. So parallelogram is a quadrilateral with, so let's call this quadrilateral A, B, C, D. So it is a quadrilateral with both pairs of opposite sides parallel. So AB is parallel to side CD and AD is parallel to side BC. Right, so the first property that we know, so I'm just going to list the properties at the bottom here. Both pairs of opposite sides parallel, right? The next property is that both pairs of opposite sides are equal. So that means the length of AB is equal to the length of CD, and the length of AD is equal to the length of BC. So for example, if the length of AB is 20 centimeters, then that is correct. You guessed it correct. The length of CD will also be 20 centimeters as well. Both pairs of opposite sides are actually equal to each other. So let me just write it down. Both pairs of opposite sides are equal, right? In terms of the interior angles, of course, with any quadrilaterals, we know that the sum of the interior angles of any quadrilateral is 360 degrees. But with regards to a parallelogram, opposite angles are equal. Both pairs of opposite angles are equal. That means angle A is equal to the size of angle C. So for example, if angle A is 115 degrees, angle C will also be 115 degrees as well. And angle B is equal to the size of angle D. So what can we conclude? We can say that both pairs of opposite angles are equal. Now, with regards to the diagonals, and I mentioned what a diagonal is, it basically goes across from one vertex to the other. So I have two diagonals in this parallelogram. I have diagonal AC and I have diagonal BD. Right? So with regards to the diagonals of a parallelogram bisect each other. That's a new word to you. The word bisect, bi meaning two, it basically means that they cut in half. So let's say they intersect at a common point E. Intersect means that they both cross each other at point E. So the diagonal AC intersects with the diagonal BE, and they intersect at point E, and they cut each other. So the length of AE is equal to the length of CE, and the length of DE is equal to the length of BE, right? And of course, you can see that there's vertically opposite angles there as well. But the diagonals of a parallelogram bisect each other. The diagonals of parallelogram, or the diagonals bisect each other, right? So those are the properties of a parallelogram. The next shape we will be looking at is a rectangle. Now I'm just going to make a sentence or state a sentence, and which might sound confusing at first, but it makes a lot of sense if you think of it, right? A parallelogram is not a rectangle, but a rectangle is a parallelogram. Or I can rather phrase it as a rectangle is a parallelogram, but a parallelogram is not a rectangle. Now you might say, that does not make any sense at all. What am I saying? Basically, a rectangle, right, has all the properties of a parallelogram, but more, right? So it meets the minimum conditions to be regarded as a parallelogram, but there's more conditions to it. So let's look at a rectangle, and I'll get back to it now. So I also wanted to quickly discuss, and I remember I said before I forget, let me just state the conditions to prove that something is a parallelogram. There's actually three. If I can prove that both pairs of opposite sides are parallel, then the figure that I'm given is in fact a parallelogram. And I can take my pencil and I can mark all the other properties onto the diagram. If I can prove that both pairs of opposite sides are equal, then I have proved that the quadrilateral is in fact a parallelogram. And the last condition, if I can prove that one pair of opposite sides are equal and parallel, then it is a parallelogram as well. So those are the three conditions to prove that a quadrilateral is a parallelogram. But back to the interesting stuff of a quadrilateral, we said that a quadrilateral is in fact a parallelogram. So let me write that down. Right? So we're looking at the rectangle. Right? Let's define a rectangle before we draw a rectangle. We said a rectangle, it is a parallelogram, meaning that it is a quadrilateral with both pairs of opposite sides parallel, right? But now what differentiates a rectangle from parallelogram? A rectangle has interior angles that are equal to 90 degrees, with each interior angle equal to 90 degrees respectively, right? So each angle is equal to 90 degrees. And I'm sure that you have come across a rectangle in your life before, or the shape or the outline of a rectangle before. So let's quickly draw a quick sketch of a rectangle. Just a quick sketch, right? So a rectangle looks something like this. Okay. A rectangle looks something like this. Let's call this rectangle A, B, C, D, E, F, G, H. Right? Let's call this rectangle E, F, G, H. Right? Now, it meets all the properties of a parallelogram because it is a parallelogram. So both pairs of opposite sides are equal. Both pairs of opposite sides are equal. right? That means the length of EF is equal to the length of GHG, and the length of EH is equal to the length of FG. Both pairs of opposite sides are parallel. So both pairs of opposite sides are parallel. So EF is parallel to GH, and EH is parallel to FG, right? And what else do we know? Both pairs of opposite angles are equal. And they, of course, they have to be equal because of the definition of a rectangle. Each interior angle is equal to 90 degrees. So angle E is equal to 90 degrees, angle H is equal to 90 degrees, angle F is equal to 90 degrees, and angle G is equal to 90 degrees, right? And of course, 90 plus 90 plus 90 plus 90, the sum of angles of quadrilateral is 360 degrees. Opposite angles are equal. And what's also fascinating is whenever you see parallel lines, what should pop into your head? Fun. F corresponding angles. Okay, sorry about that. F corresponding angles, U co-interior angles, which are supplementary, and N alternate angles, which are equal when, of course, the lines are parallel, or it lies between parallel lines. Now, in this case, I can see that there's two parallel lines here, and there's two parallel lines here. I can see that 90 plus 90 is 180 degrees. Co-interior angles are, in fact, supplementary, the U shape. So it's quite interesting to bring geometry of straight lines into geometry of 2D shapes as well. So you cannot forget that content. Now, with regards to the diagonals, again, the diagonals of a rectangle bisect each other, but with a rectangle, there's something very, very fascinating that happens. The diagonals does not only bisect each other, but they are also equal in length, right? And that is mainly caused because of the hypotenuse are both equal in these two respective triangles. And using the theorem of Pythagoras, the length of EG will be equal to the length of F8. So some of you might have lost me with that last statement, but basically if you look at this triangle, it's a right angle triangle, triangle EGH, and if I look at triangle, what is this? Let's say triangle EFG. These are two right angled triangles, and so if you use the theorem of Pythagoras, which basically states that the hypotenuse squared is equal to the sum of the square of the other two sides, then of course the diagonals will be equal in length. But of course they also bisect each other. So let's say they intersect at common point A, B, C, D, E, F, G, H, I. Let's say the common point of intersection is point I. So the length of this diagonal, the length of EI will be equal to the length of GI, and the length of IH will be equal to the length of FI. But do you notice that they all have the same length? Why? Because the diagonals are equal in length. So I can say that the diagonals are equal in length, right? And of course the diagonals bisect each other, just like a parallelogram. So you can see that all the properties of a parallelogram apply to the rectangle, but all the properties of a rectangle does not apply to a parallelogram. Now, moving on from there, we'll move on to the square, right? So square is actually quite an interesting shape as well. So a square is basically a rectangle, right? With all sides equal. So a square is a rectangle, but a rectangle is not a square. Why? Because rectangle may not necessarily have all sides equal. The properties of a rectangle is that opposite sides are equal. Both pairs of opposite sides are equal. But a rectangle meets every single property of a square meets every single property of a rectangle. So I can define a square it is a rectangle with all sides equal. Right? It is a rectangle with all sides equal. So let's just quickly draw a square like such. Just a quick sketch of a square. As accurately as I can. Okay. So if I look at this square, let's call it square A, B, C, D, something simple. Again, it meets all the properties of a rectangle. So basically, a square is also a parallelogram, but a parallelogram is not a square. So we know that both pairs of opposite sides are equal and parallel, right? Very similar to parallelogram, parallel, right? Should have only one R in it. So both pairs of opposite sides are equal and parallel. So actually, that is true, but let's just say both pairs of opposite sides are parallel for now. I'm just realizing that it's sort of a given that both pairs of opposite sides will be equal. Why? Because all sides are equal in length. All sides are equal in length. So what does that mean? It means that if the length of AB is 5 centimeters, the length of BC will be 5 centimeters, and the length of CD will be 5 centimeters, and the length of AD will be 5 centimeters. They are equal in length. And of course, we know just like a rectangle, and we also said that the opposite sides are parallel, of course. And just like a rectangle, each interior angle is equal to 90 degrees. To 90 degrees. And what about the diagonals? Just like a rectangle, the diagonals intersect at the diagonals bisect each other, but the diagonals are also equal in length. So the square, the diagonal is actually doing quite a lot, and I'm going to explain why in a minute. Let's say we have two diagonals here, A, B, C, D, E. So let's say they intersect at point E. So the diagonals are equal in length, and they bisect each other, right? And so let's write that down. The diagonals bisect each other. Diagonals bisect each other. And the diagonals actually intersect at 90 degrees. And you can also think of it as that the diagonals are perpendicular to each other. The word perpendicular means that they meet or they intersect at 90 degrees. So they intersect at 90 degrees. Of course, if this angle is 90 degrees, this angle is 90 degrees, 90 degrees, 90 degrees, the angles in a revolution is 360 degrees. So the diagonals actually intersect at 90 degrees, which I find quite interesting as well. So the diagonals intersect at 90 degrees. I think a better way to phrase this is that the diagonals are perpendicular to each other. So the line or the line segment AE is perpendicular to BD, right? And the last, really the last property of the square is that the diagonals does one more trick, and that is it bisects the angle. And if you can recall, the word bisect means cut in half. So let's look at angle A. This diagonal cuts it in half. So this part is equal to this part. And of course, if it's 90 degrees, 90 degrees divided by 2 is 45 degrees. So this part is 45 degrees. This is 45 degrees. Angle D is cut in half. So this is 45 degrees, 45 degrees. So the entire angle D is equal to 90 degrees. Angle C, we have 45 degrees. 45 degrees, the diagonal is cutting it in half, and angle B as well, 45 degrees, 45 degrees. So we can say that the diagonals bisects the interior angles. Right? It bisects, it cuts it in. half. So those are the properties of a square. Now let's move on to the rhombus. So the rhombus is quite interesting. It's like having a square that's drunk. It's just slanted to the right or to the left. So it's basically a square that's tilted. That's the informal definition to think of it. So let's look at a rhombus exactly. So what is a rhombus? Quite an interesting word as well, a rhombus. I like to define a rhombus as a parallelogram with all sides equal. Now you might say, a parallelogram with all sides equal, isn't that a square? Well, a square can also be defined as a rhombus with each interior angle equal to 90 degrees. I think that's also quite a good definition of a square as well. And I'll explain what I mean later on. So a parallelogram, so a rectangle, it is a parallelogram. I'm going to use this form to show you parallelogram with all sides equal. So that being said, a square is a rhombus, but a rhombus is not a square, right? A rhombus does not have each interior angle equal to 90 degrees because it's tilted. And because it's tilted, that interior angle will no longer be 90 degrees. It will either form an acute or an obtuse angle. So let's look at the properties of a rhombus. Let's look at the properties of a rhombus. Let me just draw this as accurately as I can. Okay, that's about a. Right, so let's say this is something of a rhombus, right? There shouldn't be an extra part here, but that's just a quick sketch. Let's say this is A, B, C, D, right? This is rhombus A, B, C, D. Now we said that it is a parallelogram, so it meets all the properties of parallelogram, but in this case, all sides are equal in length, right? But can you see that these angles are clearly not 90 degrees anymore because it's tilted? So the first property is that all sides are equal. And since it is a parallelogram, of course, the both pairs of opposite sides will be parallel. So both pairs of opposite sides are parallel, right? So AB is parallel to CD and AD is parallel to BC. Yeah, BC is parallel to AD. Now, moving on from there, we can see that it's a parallelogram. So again, the interior angles will no longer be 90 degrees respectively, as a square is, but opposite angles are equal, very similar to a parallelogram. So both pairs of opposite angles are equal. Both pairs of opposite angles are equal, right? And now let's look at the diagonals. Now I find the diagonals of a rhombus very interesting, and it's nice to actually do an investigation in class if time permits, or you can do an investigation on your own and you can just check this out for yourself, or maybe on Sketchpad or GeoGebra if you like. So if I have a square, let's go back to our square. If I have a square and if I tilt the square, because the informal definition of a rhombus is that it's just a square that's tilted, right? If I tilt it exactly the same, this angle, the angle that's formed when the diagonals intersect each other, will still be 90 degrees. And I think that's absolutely fascinating as well. So the angle, let's say they intersect at point E, the angle is still 90 degrees, right? So the diagonals, yes, they bisect each other, but unlike the square and the rectangle, the diagonals are not equal in length. I'm not sure if I mentioned that here, so let me just add on to the square. They bisect each other and are equal in length. So don't forget, a square and a rectangle, the diagonals are equal in length. But with the rhombus, the diagonals are not equal in length. So the length of AC will be different to the length of BD, right? The diagonals, yes, they bisect each other, very similar to a parallelogram, but they intersect at 90 degrees as well. So the diagonals bisect each other. Again, they are not equal in length, and the diagonals intersect at 90 degrees. Or you can say that the diagonals are perpendicular to each other. And just very similar to a square, because remember, a square is a rhombus, very similar to that, the diagonals of a rhombus bisects each angle. So let's say the angle that's formed here is 120 degrees. So the angle here will be 60 degrees and 60 degrees. Just as an example, it could be something else. And this will be the same as that. And this diagonal would bisect these two, angle D, and the diagonal will also bisect angle B as well. So the diagonals bisects the angles. Right. So those are the properties of a rhombus. Now, moving on to the next figure, let's look at a trapezium. A trapezium should be most students' favorite quadrilateral. Why? Because there's only one property for a trapezium. The trapezium looks something like this. Right? You also get something called an isosceles trapezium, which I'll explain if I do not forget. But let's say we have a trapezium that looks something like this. Right? So let's say we have the trapezium D, A, B, C, D, E, F, G. Right? It only has one property, and that basically defines a trapezium. A trapezium is a quadrilateral with one pair of opposite sides parallel. Only one pair, right? Not two pairs, only one pair. So we can define it as a quadrilateral with one pair of opposite sides parallel. And I believe if it's not America or the UK, I think it's America who calls it the trapezoid as well. But an isosceles trapezium is a trapezium with a quadrilateral with only one pair of opposite sides parallel with two sides equal. And isosceles, where did you hear that from? When we looked at the isosceles triangle. Remember, an isosceles triangle is a triangle with two sides equal and two base angles equal. Basically, the angles that are opposite equal sides are equal. So that is a trapezium, and that ends there. With a trapezium, what type of questions can you expect? I could give you an angle here, and this angle could be missing. For example, let's say, just as an example, this is not part of the properties, but let's say as an example, this is 120 degrees, and this is x, and I ask you to solve for x. And I know that this is a trapezium, right? Because these two sides, of course, are marked parallel, and I can see a U shape. Whenever you see parallel lines, specifically with these geometric figures, like a parallelogram, a rectangle, a square, a rhombus, you always need to keep fun in mind, corresponding angles, co-interior angles, and alternate angles. So of course, co-interior angles are supplementary, they add up to 180 degrees, so x is, in this case, is equal to 60 degrees, right? Because they are co-interior angles. Co-interior angles, and you need to include the lines that are parallel. So it's co-interior angles DE parallel to GF or FG. Remember, with geometry, for every statement, there has to be a corresponding reason for it. Now, the last special type of quadrilateral that we will be looking at today is a kite. So I hope that you had quite a fun childhood and was able to play with a kite in the wind. A kite with sort of looks like a diamond shape, looks something like this. Right, it looks something like this. I'm just going to draw a quick sketch of this, nothing too fancy or precise, but I want it to look as much as a kite, as much of a kite as possible. So a kite looks something like this, right? Like a diamond type shape, right? Let's say this is kite ABCD, right? Something simple. That's not complicated. That's not complicated, right? It's kite ABCD. So kite, the first property of this geometric figure, and if I can write some in the side here so it looks next to each other, is that both pairs of adjacent sides are equal. So the word adjacent basically means next to something. So both pairs of adjacent sides are equal. So both pairs of adjacent sides are equal. So what does that mean? It means that the length of AD is equal to the length of AB, and the length of CD is equal to the length of BC. Right, okay. The next property, let's get into the interesting stuff, the diagonals, because the diagonals play quite a large part, quite an important part with the kite. So there's two types of diagonals. You get the main diagonal and not main diagonal. Basically the longer diagonal and the shorter diagonal, right? So in this case, it's clear that the longer diagonal would be the one that's vertical, AD, or the one that's, of course, visually longer. And the shorter diagonal is BD. So what's interesting about these diagonals is that the diagonals intersect at 90 degrees. So the diagonal AC is perpendicular to the diagonal BD, right? I hope that you can just press pause on this video and take your time. I hope this is not information overload. Just do one quadrilateral at a time. I recommend that you don't memorize the properties. Of course, you need to know it, but don't memorize. What do I mean? Don't create abbreviations and stuff. Just create a diagram and do what I'm doing. Mark all of it with your pencil and practice over and over again. And you should get it. You can apply it to the geometric figures that you have. So moving on from there, we said that the diagonals intersect at 90 degrees. The diagonals are perpendicular to each other, right? And another property is that the diagonals do not bisect each other. Be careful. But the longer diagonal bisects the shorter diagonal, right? The longer diagonal, let's say they intersect at point E. The longer diagonal cuts the shorter diagonal in half, right? So the length of DE will be equal to the length of BE. So I can say that the longer diagonal bisects the shorter diagonal, right? And that's not true for the longer diagonal. The length of AE is not equal to the length of CD. It's only the longer diagonal that bisects the shorter diagonal, right? And also the longer diagonal, it actually, right? So let me get this right. The longer diagonal bisects the angles. So meaning if this is angle A, it cuts it in half. And if this is angle C, it cuts it in half. I'm not saying that angle A is equal to angle C, no. I'm just saying that whatever this angle is, let's say this angle is 60 degrees, then this will be 30 degrees, 30 degrees as such, right? So I can say that the longer diagonal bisects the angles, right? And the last property of a kite is that the angles that are opposite the longer diagonals are equal to each other. So angle B is equal to the size of angle D. So angles opposite longer diagonals are equal. So those are the properties of kite. Now you might notice that I do not have any page near me to list these properties, right? I did not memorize it by creating abbreviations. The easiest way to learn or to know the properties is draw these figures on yourself. Draw a kite and just take your pencil and mark the properties on your own. And that is how you'll be able to list and know the properties. And the types of question that you could expect is something like this, where I'll give you a geometric figure and I'll tell you that this is a trapezium, or give you a geometric figure and I'll tell you that this is a rhombus. And you need to find X, Y, and Z, the missing length or the missing angles. So you need to know the properties. You also need to know geometry of straight line, fun, corresponding, co-interior, and alternate angles. So revise over these properties, and I trust that you will do well. Thank you, grade 8s, for your time.